We'll go into a little bit more of channel sounding. We'll look at some analysis of the channel sounding. I'm going to do a bit of an intro. We'll talk about some use cases, some concepts, which Damon already addressed, so I may skip a few slides. And we'll go into the link layer where we can answer some of the questions that were asked. And we'll do some analysis and we'll go do a summary. So a little bit of background on myself. I'm the CEO and founder of Packetcraft, but I am also a software developer by trade. Done a lot of work in the link layer. In fact, I'm just curious here, is there any other link layer developers here? Anyone developed in the link layer? Okay, you guys aren't raising your hands, but I know there's a few out there. We're going to talk about the link layer. So this is the packet organization in terms of, okay, now we know what the packets look like. Oh, I'm sorry, actually, I forgot one thing on this previous slide. Along with a channel sounding packet, there's a tone that happens at the, either you have a tone, so if you look at the, do I get a pointer here? I don't get a pointer here. But you can see the diagram on the bottom. You see the CS sequence, that's the data packet. And you can either have a tone that follows the CS packet or you have a tone that precedes it. Okay, so channel sounding is just a packet, or it's a tone in a packet, or a packet in a tone. Okay, so that's what that looks like. Okay, let's look at the organization of these packets over the air. Okay, so, and I think this was a question earlier too about can you send data over channel sounding? It's yes and no. So channel sounding itself does not carry data, but it happens in the context of a connection. So you can actually send data in the connection or the ACL normally, but the channel sounding procedure actually fits inside or between a connection event. Okay, so over here, the blue is the new channel sounding transport. We have the channel sounding procedure. There's one procedure that fits inside of a connection event. And then you have one or more channel sounding events that make up a procedure. And then you have one or more sub-events that fit into an event, a channel sounding event. And then you have many steps that fit into a sub-event. Okay, so that's the organization. This is a LSIS air trace of a channel sounding operation between two peer devices. Note what I highlighted in blue, or everything here is a procedure between two devices. What I highlighted in blue is actually the 4.x or the 4.0 security. So the secure connection is actually a prerequisite, and it's required by channel sounding. You have to be in a secure connection to even start channel sounding. So what happens in the channel sounding procedure? We exchange capabilities. So each device is going to have different capabilities. The Bluetooth channel sounding spec has quite a bit of range so that it can support many, many different devices capabilities. So we have to exchange capabilities. We exchange security information. So all that, there's a lot of pseudo-random operations happening to avoid or to sort of thwart the man-in-the-middle attack. And so we have to exchange some security parameters. And then we negotiate a configuration. We settle on the timing and certain capabilities of both our devices. And then we start exchanging measurements. So these are the tones, the mode 0 to mode 3, the exchanges. And then we can start sending reports up to the host or to the upper layers to actually run the algorithm. And the exchange of measurement is what exchanges, or we want to do that repeatedly, right? So we may do an exchange across all the channels in one procedure, and then we may do another procedure, and we want to do it again and again to sort of constantly improve the algorithm. Or in the case we're walking and we want to measure someone walking, we can constantly be measuring. Okay. Here's another view. This is kind of diving a little bit deeper. We did talk about steps. So the diagram on the right there is actually channel sounding steps. And what I want to point out in this diagram as we analyze this is a lot of the anti-spoofing that's built into the spec. I mean, most of the spec, maybe like just rough numbers, 80% might be having to do something with security and anti-spoofing. So a lot of security is built into the spec. like for example, pseudo-random channels. So this is like selecting which frequency are we going to run a step on. Well, if you look at the boxed red item on the right where it says RF channel, you'll see that each step is actually on a separate channel. So now it's making it even harder. So we said this is, which hotel are we in, right? So for every step, if we're moving at different locations, it's a lot harder to find and locate and spoof channel sounding operations. Well, the next is pseudo-random access address generation. That's the long column on the left there. Every step is on a different access address. So each name of the packet is changing on every single step. Okay, and then the next two, sub-event, sub-mode insertion, and tone slot, extension slot present. I kind of highlighted the timing on the bottom. This is time. This is like, because the packets are elongating in certain times, it's going to be difficult to sync on the start of a packet and start participating or listening to all the packets if you don't know how long the packets are. So that's time, space, and coding. Three of the four things that you need to have communication with a peer is constantly changing on each step. So very hard, very difficult to spoof. And in addition to those four that I mentioned, there's also antenna path permeance. So if you have multiple antennas, we're constantly changing antennas. So even if you're able to receive, you don't know which antenna it comes from, so your calculations will be off. The pseudo-random sounding sequence markers, this is the contents of the payload. We can actually, if you don't have the right sequence, you're going to be sending the wrong sequence or listening to the wrong sequence, and the random bit sequence as well is part of the payload. NADM, the normalized attack detect matrix. So now it's kind of difficult to know. So if you're in an RF environment, sometimes the RF environment itself may be inducing noise on the packet, or it could be an attack. So there is configurability in your application. So let's say in the car access case, you really want a very high sort of setting for the detect matrix for attacks, right? So as you start seeing packet, there's a formula in the way you calculate this. If you start not receiving packets, or if the packet has some corruption in it, this number gets higher, right? So it's a way to determine how much of the probability of being attacked. And so you probably want to use a high number, say if it's your car, you don't want someone driving with your car. But if you put some sort of, I don't know, like maybe something what's less secure, maybe the cookie jar, put some sort of lock on the cookie jar, and maybe it's not all that important to, actually if your kid figures out how to break that security, maybe just let them have the cookie. But so you can actually determine how much security you want before with NADM. Okay, so let's summarize. High accuracy, so channel sounding has high accuracies with about 30 centimeters with specialized algorithms. So the algorithm is important to actually calculate the accuracy. The ubiquity of Bluetooth. Beacons today already do indoor positioning, but with fine ranging, adding that to the beacons can improve that. Your phone is your digital key, and we've also seen that earlier about how the phone can be part of that key that unlocks your door, unlocks access to your office. Highly secure with built-in anti-spoofing. So a lot of good things to come, right, with channel sounding. And